Hello, and welcome to another edition of Coffee Cats. This series is on basic soil testing and soil fertility, and this episode is going to cover interpreting soil test results. If you haven't seen the other episodes in this series, please check those out. So soil testing is four separate activities: soil sampling, analyzing that soil sample that you collect, interpreting the results from the analysis, and making recommendations. And this episode specifically would deal with interpretation of results. So when we're interpreting the soil chemical analysis, some people look at this over here on the left as how they view it. You know, there's a certain point above which plant nutrients are available, and below that they're unavailable. But this isn't true. A correct interpretation of soil is of increasing availability. So phosphorus or potassium or whatever you're testing for, there's this total amount in the soil, and as there's more and more, it becomes more available. And each chemical analysis that we discussed previously kind of takes a different slice of that pie. Modified Morgan takes just a very little bit of the phosphorus out. Bray a little bit more, and Mehlich 3 quite a bit more. And so if you take the same soil sample and you send it to a lab that runs Bray, you might get a result of 15 parts per million. And with Mehlich 3, you would get a result of 30 parts per million, twice as much. But for that chemical analysis to be useful in any way, we have to have locally conducted soil test correlation. And so correlation is simply the relative yield versus soil test, and the point on that soil test scale above which a plant no longer responds to application of an element or that essential nutrient. And so we have to conduct this experiment at multiple sites with multiple soil test concentrations to get a correlation curve like this. So here in this example data, we see a soil test result on the horizontal scale, and on the vertical scale relative yield. And relative yield simply is just the unfertilized plot divided by the fertilized plot. So you go out into a field to say soil test of 50, and you set up a couple of replicated plots. And you put on plenty of phosphorus on one plot, and you put no phosphorus on the other plot. You take the yield of the unfertilized plot and the yield of the fertilized plot, you divide the fertilized plot into the unfertilized plot, and you would probably get a relative yield close to 1, because at 50 we don't really expect a response to fertilizer. But if your soil test was down here in the single digits, that unfertilized plot might have a yield that is half of the fertilized plot. And so your relative yield would be 0.5. And so when we're doing a correlation, we're really trying to relate soil test to yield to get a relationship between plant performance and nutrient concentration in the tissue. Now, if we go back to one of the earlier episodes where we talked about what makes a nutrient essential and how plants acquire nutrients, you'll remember that deficiency is the point on a curve as nutrient concentration in the tissue goes up, plant performance increases. Sufficiency is the point beyond the critical concentration where adding more nutrients in the tissue doesn't increase performance. And so now we're one step away from this, and we're saying as the soil test concentration goes up, the nutrient concentration goes up. And similarly, there's a critical level in the soil test, that when we apply nutrients beyond that critical level, we don't get any improvement in yield or plant performance. One of the problems with soil test correlation is, this is kind of a ballpark number. And so when we do it across many sites across the whole state, there's different places where we can put that critical level, and it can vary from field to field. And so what we report as the critical concentration is really an average for the whole state. And so your best bet is to keep track of your fertilizer inputs in your soil test and kind of determine it, on your own based on your records, where exactly it would be in your specific situation. Now, calibration is the other part of making that soil test result usable. And so calibration asks the question, how much fertilizer do I need? And so this has to be performed at multiple sites so that we get a range of soil tests. In this example on the right, we see the blue line represents a field with a soil test of 30, the orange a soil test of 20, and the gray a soil test of 10. And it doesn't really matter the units or what kind of soil test. This is just a relative example. And we see that for each of those soil test values, so 3 different fields, we went out and we put a range of fertilizer rates. So you could think about this as a phosphorus study where we would apply 6 or 7 different rates of phosphorus. And we look at what the yield, how much phosphorus it took to maximize yield at that site. And so we do this across many sites, and we figure out at a given soil test how much fertilizer is required to maximize yield. Well, as you might imagine, as the soil test value increases, the amount of fertilizer required to maximize yield decreases. And that rate that maximizes yield is what we call the sufficiency rate. It's the amount of fertilizer that provides sufficient nutrients to maximize yield. So in summary, most labs that use the same method should report the same soil nutrient content. So if you took your sample and you split it and sent it to 3 different labs and they were all running the exact same method or protocol for malic-3 extraction, you should get pretty similar numbers. But the results, when you get different results in fertilizer requirement from different labs, that's based on this interpretation. And so a soil test can only provide an index of relative nutrient available. To be useful, that soil test requires local correlation and calibration data. And often, many of the private labs are using publicly available correlation and calibration data sets that were conducted by universities many years ago. There are a few private labs that have done correlation and calibration data. In the next talk, we're going to talk about the soil test philosophies and why, even though they're using the same correlation and calibration data and the same soil test method, they may come up with different fertilizer recommendations.